I have a problem here. It says a battery delivers a terminal voltage of 12 volt at open circuit, but its terminal voltage, there shouldn't be a comma here, voltage drops to 10.8 volts when connected to a 4 ohms resistance. So we have to find the Thevenin's equivalent circuit for the battery. So basically, uh, let's say this is the battery, like that. I will draw the battery like this, maybe just the symbol, and when it's connected, when it's open circuit, the voltage here is 12 volts, but when it's connected to a 4 ohms resistance here, then the voltage drop here is 10.8 volts. So the voltage drops somewhere, and where it drops, it of course it drops in the internal voltage, internal resistance of the battery. Every battery, there is no ideal battery, so there is an internal source. In an ideal battery, the internal resistance will be 0, but in a real battery there will be a finite internal resistance. We have to find that. So basically we have to find the voltage of the battery, which is, when we say Thevenin's equivalent of the battery, so what is the actual voltage of the battery and what's the internal resistance. So that's the internal resistance. So basically these things we need to find out. VPC, let's call battery, I don't know, just a symbol. So we have the information, so let's draw the battery with the internal resistance now, and this is the internal resistance. Let's call it R internal maybe, and this is V battery, VBC, and this one is, normally this one is 12 volts when it's open circuit, but when it's connected to a resistance of 4 ohms, then the voltage is 10.8 ohms, 10.8 volts. So now the voltage is 10.8 volts. So the remaining voltage, this is 12 volts minus 10.8 volts, that voltage is dropped here. So this one, the voltage drop is 1.2 volts, and since this is 10.8 volts and we know the resistance, we actually can find the current. What is the current the battery is supplying? We can find that. So that will be the voltage 10.8 divided by 4, so that's 2.7 amps. So that's the value of the current. So now we have the value of the current, and we also know the amount of voltage that is dropped across the R internal, the internal resistance of the battery. So that one is 1.2 volts. So we can find the value of, so value of the internal resistance. So this is the drop across the internal resistance, which will be R internal times the current, 2.7 amps. So if we do that, it becomes like 0.44 ohms, something like that, 4444. So I'm just writing 2 fours. So that's the internal resistance, and of course the VBC will be 12 volts. So when we draw the Thevenin's equivalent circuit of the battery, it will be this one 0.44 ohms, and this is 12 volts. That is like that. But whenever a load is connected, this voltage is dropped according to the value of the loads, because according to the value of the load, there will be a flow of current. If the load value is very high, the flow of current will be small, and the drop here will be very small. So the voltage that will be available here will be nearly close to 12 volts. But when the load is very small, if the load is equivalent to this one, let's say the load that is connected here is also 0.44, then half of the voltage will be dropped here. So that's how it works. And so this is the Thevenin's equivalent of the battery. And we can see that when nothing is connected, no load is connected, the voltage here is 12 volts, because there is no flow of current, so there is no voltage drop across the internal resistance.